Hello and welcome to our webcast. Today's topic will be displacement ventilation. My name is Randy Zimmerman and I'll be presenting today's program. I'll be joined later by Jim Oswegen and James Gray for the question and answer session. Jim is also a Titus Chief Engineer with over 45 years experience, and James is the product manager for all Titus grill, register, and diffuser products. In today's program, we'll start out talking about basic system concepts, and then we'll look at how displacement ventilation diffusers work. We'll also look at typical applications, design procedures, and product selection. Along the way, we'll use smoke videos and other tools to help demonstrate the air patterns created by displacement ventilation. Let me assure you that the purpose of this webcast is not to sell displacement ventilation as the best system for every building. We'll discuss the reasons why certain applications are recommended while others are not, but it's important to consider displacement ventilation as one more possible solution. I like to think of displacement as one more tool in my toolbox of air distribution systems. We should start by explaining the difference between conventional overhead systems and displacement ventilation. Conventional overhead systems provide comfort through room air mixing. For this reason, these systems are also known as fully mixed systems. In typical cooling applications, 55-degree air is supplied from ceiling diffusers or high sidewall grills. The induction created by the outlet discharge jet results in room air motion. This so-called secondary air motion is due to the entrainment of room air into the supply jet where mixing occurs. Ideally, an overhead system results in fully mixed air throughout the occupied zone with minimal temperature stratification. It's important to note that in a system like this, the first thing our supply air does is pick up heat from the overhead lighting. This is one reason why we typically need to supply a 20-degree delta T on our supply air. We'll see in a moment why higher supply temperatures not only work well, but are actually recommended for displacement systems. Displacement ventilation takes a very different approach to providing comfort in the occupied zone. Instead of trying to eliminate temperature stratification throughout the space, displacement takes advantage of the natural buoyancy of air to create stratification as warmer air and pollutants rise towards the ceiling. For this reason, displacement systems are also known as fully stratified systems. In our industry, the word stratification often carries a negative connotation, but that's not really fair. So long as the temperature gradient in the stratification zone isn't excessive, we should achieve comfort in the occupied zone. Now that we know what displacement is, let's look at how it works. Displacement systems typically supply 63 to 68 degree air through specially designed diffusers that are located on low side walls. This cool air discharges at less than 80 feet per minute from the face of the diffuser and quickly cascades down to the floor. The air continues to move slowly across the room in a layer about 4 inches deep until it locates a source of heat or an obstruction. In office applications, the heat sources in the occupied zone are usually people and equipment. When the slow-moving pool of air encounters a heat load, it quickly rises and carries the heat and pollutants towards the ceiling. Internal heat loads and contaminants are then carried away by the return air. We refer to this as a thermal plume. In order for displacement ventilation to work most efficiently, the return air should be pulled from well above the occupied zone, preferably from the highest point in the room. Since much of the heat load from overhead lighting is captured from above the occupied zone and supply temperatures are higher, you should expect higher return air temperatures than would be found in a conventional mixed air system. In order to avoid potential humidity issues and air quality concerns, we need to limit our relative humidity to 60% or less. There are many strategies we can employ at the air handler, or we might choose desiccant dehumidification. If we choose to drop our air temperatures to 55 degrees to wring the moisture out of the air, we can blend return air with the supply air to bring it back to 65 degrees. Now let's look at a live demonstration. We'll use theatrical smoke to help you see the characteristics of the air pattern created by displacement ventilation. The temperature in our throw room is controlled to maintain 73 degrees, and the supply air temperature will be 65 degrees. As soon as we remotely switch on the smoke generator, you'll be able to see the cool air cascading down the face of the diffuser. Now look at the way it moves across the floor. I've often heard it described much like water being poured from a bucket. If it doesn't find a heat load or doesn't bump into an obstruction, it could easily cover up to 30 feet before it runs out of velocity. Now let's look at a displacement diffuser supplying a room with a heat source. While there are many application guides and brochures available from manufacturers, the most reliable sources for highly detailed information regarding the science behind displacement ventilation are non-commercial publications from ASHRAE and REVA. These publications are the result of industry-sponsored research, and they have undergone peer review to ensure the accuracy of their content. I would encourage anyone looking for additional information about displacement ventilation to seek out these fine publications. The new Titus Displacement Ventilation Guide can be found on our website. It was written by yours truly and was based upon the results of ASHRAE Research Project RP949 as presented in the ASHRAE Displacement Ventilation Guide. This research was sponsored in part by ASHRAE Technical Committee 5.3 and represents the latest and best research concerning displacement ventilation. Now let's look at the theory behind displacement ventilation. In order to determine the airflow requirements for a displacement system, we need to look at all of the loads in the room and then determine how much of each load will reach the occupied zone. RP 949 provides the weighting factors that should be used. It's important to understand that loads both inside and outside the occupied zone will have differing effects on the comfort of an occupant. ASHRAE guidelines allow us to accurately estimate these effects. The total heat transfer to the area of interest, in our case the zone between the head and foot of the occupant, can now be calculated using this equation. We can simplify things a little by taking out the air volume component to get an equation that describes the resulting temperature differential from the head to the foot of an occupant. Now it's time to look at thermal comfort considerations. ASHRAE Standard 55 is often referred to as the thermal comfort standard. It recommends that for good thermal comfort, the temperature difference between the head and foot level of a standing person should not exceed 5.4 degrees. If we assume a constant floor-to-ceiling stratification gradient of no more than 1 degree per foot, any design that provides comfort for a standing occupant should also work for a seated occupant, because a seated occupant would experience no more than a 3.6 degree differential. In addition, we need to pay attention to the difference between the supply and exhaust temperatures. As a rule of thumb, exhaust temperatures should not be more than 36 degrees higher than the supply air temperatures to avoid a sensation of draftiness. Now obviously, at no more than 1 degree per foot, it would take an extremely high ceiling to get close to a 36 degree temperature differential. We can also rearrange the equation to solve for the air change rate. If we know the air change rate, then it's a simple matter to calculate the air volume. Then, rearranging the equation again, we finally have an equation to calculate the cooling volume requirement. But we're not quite done yet. If we make a few assumptions that would be appropriate for a typical office environment, we can further simplify the equation. At last, we have a simple equation that we can use to calculate cooling airflow volume to handle the effect of the total heat load on the occupied zone. Now we'll step away from the math and look at both the advantages and limitations of displacement ventilation systems. So exactly what are the advantages of displacement ventilation? Well, as we'll explain, there are several ways that displacement provides both energy savings and improved air quality for our occupants. Building owners pay higher electric bills for excess system pressure, so anything we can do to lower pressure requirements will save energy while reducing operating costs. There's a calculating tool called the cost of pressure that can be found on the front page of our website. It provides a simple way to compare the operating costs of air devices operating at different pressures on an annual basis. Although the cost may first appear small, it's important to take into account the number of air delivery devices found in typical buildings. When you start multiplying the results by hundreds or thousands of units, the numbers start getting very significant. The good news is that displacement diffusers tend to have lower operating pressure than conventional overhead diffusers, so this will help to reduce our fan energy. As you can see, when comparing the annual operating costs of our most popular ceiling diffusers to a typical displacement diffuser, the winner is clear. Operating costs could be reduced by more than 70% in comparison to a typical perforated ceiling diffuser. Now remember, this savings only applies to the diffuser operating cost, which is a fraction of the total fan energy. Displacement ventilation is known to be a way to increase comfort through improved ventilation. The goal of any air distribution system should be to efficiently deliver ventilation air to the breathing zone. For this reason, ASHRAE Standard 62.1 rates various types of systems with regard to air change effectiveness. These ratings take into account the supply and return locations as well as the discharge pattern and temperature. According to this standard, the very best overhead systems qualify for a rating of 1, and other lesser systems could be as low as 0.5. On the other hand, displacement qualifies for the highest possible rating of 1.2. This means that displacement ventilation is thought to be 20% more effective than the best overhead system, and the minimum fresh air requirement can therefore be reduced by nearly 17%. Displacement ventilation can be thought of as a single-pass system. Unlike a mixed air system that tends to distribute contaminants more or less evenly throughout the entire room, displacement uses natural buoyancy to collect pollutants at the ceiling where they can exit the room. This action results in lower concentrations in the occupied zone. In areas with mild temperatures and low humidity, economizers make use of outdoor air to reduce operating costs while improving indoor air quality. The higher supply temperatures associated with displacement could have a major impact depending on where your building is located. As most of you know, you can't simply buy a product and get a LEED credit. LEED credits are earned by increasing the sustainability of a building through the proper use of products and technology. The sort of prerequisites and credits that a properly designed, installed, and commissioned displacement system could earn would fall under the categories of energy and atmosphere and indoor environmental quality. So we've covered the advantages, but now we have to look at the limitations. From their design, it's easy to see why displacement diffusers are not generally suitable for heating applications. Slow-moving hot air would simply rise straight to the return without providing any circulation in the room. There is, however, an interesting solution to this problem, and we'll get to it shortly. Displacement ventilation also has its limits with regard to room loads. As a general rule of thumb, it's not suitable for loads greater than 30 BTUs per hour per square foot. We also know that displacement ventilation doesn't work well with low ceilings or anything that could obstruct the flow of air across the floor. There's also a very important issue we need to cover in detail, and that's called the adjacent zone. Since displacement ventilation delivers cool air directly to the occupied zone, we must be very careful not to create discomfort for our occupants. The area directly in front of a displacement outlet is known as the adjacent zone. This is defined as any area in the occupied zone where air velocities exceed 50 feet per minute at a height 1 inch above the floor. Although these areas are perfectly suitable for use as aisles or corridors, stationary occupants should never be located within the adjacent zone. While it's highly unlikely that a person passing through or stopping for a moment would notice anything, a person seated for a longer length of time would likely feel a chill in the ankle region. In order to position outlets such that we avoid stationary occupants, we need to look at the published performance data. Titus follows the industry standard by providing the length and width of the adjacent zone for both a 5-degree and a 10-degree delta T. It's important to understand that the spread of the adjacent zone can be contained by partitions and other obstructions, often resulting in longer spread in the opposite direction. On the other hand, the air pattern will simply pass around an object like a column, much like water in a stream. Now let's look at the construction features of displacement diffusers. Most displacement diffusers have a few parts in common. They all include a rear plenum assembly and a faceplate that's perforated with either round or rectangular holes. While some manufacturers simply provide perforated baffles or splash plates inside their products, other manufacturers choose to include a central baffle fitted with adjustable air pattern controllers. Diffusers with adjustable air pattern controllers typically ship out in a default position that provides a standard radial air pattern. In order to allow easy access for field adjustment, the faceplates must be removable. Although diffusers with this feature are designed to be adjustable, it's still advisable to make product selections based on the standard radial pattern. At this point, you may begin to wonder why adjustable diffusers are recommended at all. Well, the answer is easy. Adjustable diffusers are recommended because of the adjacent zone. It's important to provide some means of fine-tuning the air pattern. As anyone in the construction industry knows, things don't always work out perfectly, and sometimes spaces change purpose. For these reasons, adjustable diffusers are recommended to accommodate changes in room layout or seating locations. In this example, we show how several seating locations around the conference table would likely fall into the adjacent zone of a standard radial pattern diffuser. Then we show how adjustable pattern controllers could be set to kick the air along the walls and away from the occupants. With non-adjustable diffusers, it would be completely up to the designer to select a product that would avoid any comfort issues, and there would be no flexibility for future needs. When I think of displacement ventilation, I'm thinking big spaces because these are absolutely the best applications. Any spaces with room heights greater than 9 feet and enough open floor space to allow the proper air pattern to develop should be ideal. If the space will be occupied by moving people like visitors to a museum or travelers walking to a departure gate, that's also ideal because the adjacent zone shouldn't be an issue. In a restaurant or casino that may permit smoking, the air quality in the breathing zone could be significantly improved by displacement ventilation. Classrooms would also benefit from the improved air quality and low noise operation of a displacement system. Now let's look at the places where we wouldn't recommend using displacement. Since displacement works best in large open spaces, confined spaces with low ceilings don't allow us to take advantage of stratification. These spaces are best handled with mixed air systems. If the heat loads are greater than 30 BTUs per hour per square foot, then we would likely create a drafty environment if we tried to use displacement. In situations where contaminants are heavier than air, displacement would also be a poor choice. This could include indoor swimming facilities where chloramine can be a problem. In a chemical laboratory, displacement could result in spilled chemical agents being brought up from the floor to the breathing level. And last but not least, displacement ventilation should not be used in conjunction with mixed air products to serve the same space. Mixed air products would likely prevent stratification from forming correctly in the room. Now let's look at a design procedure for displacement. First, we must determine the total cooling load. Then we need to look at our floor space and check to see if the total cooling load doesn't exceed 30 BTUs per hour per square foot. If that checks out, then we can proceed. Next, we must calculate the cooling volume that we'll need to handle the actual heat loads in the occupied zone. This calculation is, of course, based on ASHRAE Research Project 949. Now we go into ASHRAE 62.1 territory because we need to look at our ventilation requirements. First, we calculate the minimum fresh air requirement for the breathing zone, and then we apply an air change effectiveness factor of 1.2 for displacement. I should warn you that even though ASHRAE says that a reduction in fresh air can be made due to the form of ventilation being applied, this reduction may not be recognized by all code enforcement authorities. Now that we know our fresh air requirement, we can determine the supply air volume for our diffusers. As we would expect, this will be equal to our cooling volume. If we're not supplying our diffusers from a dedicated outdoor air system, we can use our fresh air requirement to determine the percent of outdoor air that we'll need to have at our air handler. Next, we can calculate the supply air temperature that we'll need to meet our room temperature set point. Once we know our supply air temperature, we can easily calculate our exhaust air temperature. Now finally, it's time to make our diffuser selections. I went through this design procedure mainly to reinforce and apply the theory that we covered earlier. Most engineers that I know don't have the time to go through an exercise like this. For this very reason, most manufacturers offer product selection software to simplify the process and save valuable time. Our selection software is posted on our website and available for free download. It provides several different strategies for making selections based on known parameters. If you know the heat loads in the space, our program can perform the RP949 calculations to determine the heat loads in the occupied zone along with the recommended supply temperature and air volume. It also checks to make sure that the heat loads are not beyond the recommended limits. It is truly a selection tool. You can specify the minimum or maximum number of outlets and whether they'll be located on walls or out in the space. It then recommends the products and sizes that will meet your requirements and ranks them according to the size of the comfort zone they create. We consider the comfort zone to be the floor space outside the adjacent zone of the diffuser or diffusers. While standard default terminal velocity of the adjacent zone is 50 feet per minute in our program, it can be set to whatever value meets your requirements. The program also maps out the adjacent zone and allows the diffusers to be moved around the room. Now back to the diffusers. In order to keep discharge velocities low, displacement diffusers tend to be large. Unlike overhead diffusers that drop into ceiling systems, displacement diffusers are typically located on low side walls. As you can imagine, this means that the architect and interior designer should be involved from the start in order to integrate these products into the design. Luckily, displacement diffusers come in a wide variety of sizes and styles. Matching duct covers and optional mounting bases are also available to provide a clean installation. Now let's look at what's available. This is a rectangular flush model designed to fit inside a wall. These are available in a variety of standard depths and face sizes. As you can see, this unit creates a one-way air pattern. This unit is also rectangular but designed for either flush or floor mounting. It should be said that all of these diffusers can be supplied from either above or below because it makes no difference to the air pattern or performance. This unit also provides a one-way air pattern. The next unit is similar to the previous unit, but it includes discharge openings on the side to create a three-way air pattern. This next unit also provides a three-way air pattern, but it has a curved or bow-fronted face. This look seems to be most acceptable to architects and interior designers. This unit is quite different from all the rest. It's designed to go into auditoriums and concert halls to deliver displacement ventilation from a stair riser. Another way to condition these spaces is to use small round swirl diffusers to deliver low velocity air from below the seating. I've always liked the look of this one. It provides a 360-degree circular air pattern and is most often used to create air columns in large open spaces. This model is similar to the last one, but it provides a 180-degree air pattern. There are many creative ways to integrate a unit like this into a column or the end of a wall. And here's another variation on that theme with deeper sides to create a three-way air pattern. Now we're going to look at units that are designed to fit into corners. This model has a curved face that creates a two-way air pattern. This corner model at first looks a little austere, but would probably look best in a flush-mounted installation. Oddly enough, even though the unit has a flat face, it actually provides a two-way air pattern. I said earlier that displacement ventilation is only suitable for cooling, but promised to show you an interesting way to deal with heating requirements. Traditionally, displacement ventilation has required the use of separate perimeter heat to deal with loads resulting from exterior walls and perimeter glass. This often means the use of thin tubular products, separate ducting of hot air, radiant panels, or under-window fan coil units. Well, here's an interesting solution that you might want to consider. This is a relatively new product design. We call it a dual-chamber displacement diffuser. It was originally developed by Titus for a school district in Southern California. They wanted the advantages of displacement ventilation for their classrooms, but they didn't want to use a separate system to handle their mild heating requirements. This diffuser is built with a rear plenum that can supply air through either a large displacement panel for cooling or redirect the air through a lower grill section for heating. The reduced size of the lower grill increases the discharge velocity to get the horizontal projection needed for heating. The internal diverting damper can be activated by a small electric actuator, but we're also working on a self-powered energy harvesting model that will be completely standalone and require no power or external control signal for activation. Now let's look at the dual chamber diffuser in operation. So we've covered the theory and application of displacement ventilation, and I'm sure that some of you will no doubt have a few questions. At this point, our panel will attempt to answer any questions that you may have.